Hello, this is Andrew O'Brien, Mac May, and Adam Johnson, and we're doing our presentation today on Hoare logic. Hoare logic is related to the idea of program verification. Oftentimes we talk about meta-proofs, proofs about a program language in general, but program verification has to do with proofs about a specific program written in a certain language. They make use of precise language definitions in the formal language, and we use these to prove that a program behaves as we actually want it to. And this is done, again, using Floyd-Hoare logic, oftentimes just referred to as Hoare logic. Hoare logic has a specific approach that's highly useful for doing these proofs. First, a program specification is written, and then we use compositional proof techniques to prove it, whereby each syntactic construct of the language has its own proof rule. So then we can prove the behavior of a program works correctly by proving that the syntactic constructs that the program makes use of work correctly. For program specification, the first part is this idea of making state assertions. We often think of imperative programming languages as a series of commands that alter the state of a specific machine. So key is that we can make claims about a given state the program is at a specific point, and then this is done through formal assertions. And then we also need to be able to make assertions about behavior when making a program specification, particularly this command behavior. We think of commands as mapping states from one state to another. Formally, you can think of these as the pre and the post state, and this is done in Hoare logic using this idea of Hoare triples.
In the slides on assertions, the authors provide proofs that link the specifications of programs to the compositional proof techniques that show the correctness of those programs using specifications. And the syntax of compositional means that the structure of the proofs are exact mirrors of the programs that they address. So in order to outline those specifications, you need a way to make assertions about those programs that hold true at particular points during the program's execution. So the first definition we see on the first slide for assertions is assertion itself. And we see that this is simply a mapping from state to a proposition. The authors then provide a module, EX assertions, which is for examples of assertions, AS1 through AS6. In definition AS1, we have an assertion that is a function mapping ST to x equals 3. So that's simply just assignment of a variable, a natural number variable, to an x. In definition AS2, we have an assertion that results in STX, and that it also maps STY to x. So you've got x being the result of the assertion itself, as well as the assignment for STY. In definition AS3, we have STX producing a result of 3, or STX, once again, being produced for the result of STY. In definition AS4, we have STZ times STZ mapping to STX, and the negation of STZ times STZ times S being mapped to from X. And then in AS5 and AS6, we simply have mappings to true and false, respectively. In the second assertion slide, we have the concept of implication. So that is, given the assertions P and Q, P implies Q in the case that P holds in some state where Q also holds true. So that's the simple just sort of arrow assignment from P to Q that's shown in the definition for assert implies. There's also a if and only if implication between assertions. So we see that in notation, the two-way arrow between P and Q, where P implies Q and Q implies P.
A Hoare triple informally is this idea that if there's a command C and it's started in a state satisfying assertion P, and if C essentially terminates in some final state, and this final state would satisfy the assertion Q, and again, this can be defined formally and rigorously in languages such as Coq.
The natural progression from the assertion slides continues into the Hoare triple slides. So what Hoare triples allow us to do is to talk about preconditions and postconditions. So in proving program correctness, we're not just concerned with the preconditions that enable a program to be successfully run. We're also, of course, interested in the postcondition requirements. So Hoare triples provide a syntax for mapping commands with preconditions P into postconditions Q. So this is simply notated. There's a compact notation provided where it's P in braces, C between it, and then Q in braces. So what this says is that if command C is started in a state satisfying assertion P, and if C eventually terminates in some final state, then this final state will satisfy the assertion Q. So once again, this is showing both the precondition and the postcondition requirements for that command to be successfully run. So we see this in the first slide on Hoare triple's definition. Hoare triple, we see that P is assertion, C is a command, Q is an assertion, and then that maps for all ST and ST prime. ST is equal to C, maps to ST prime, maps to PST, maps to QST prime. So P being the precondition is related to ST, which comes before the command, and then Q is an ST prime, which maps to the ST prime that's produced after the command is executed. And you see the simple notation below that. We've also provided some very simple examples here that show the truth value precondition, and then x being equal to 8, and then the postcondition x is equal to 8. In the second example, we see x is equal to y. The precondition x is equal to x minus 2. Because x and y are equal, you can have a postcondition of x is equal to y minus 2 because it is equivalent to the precondition of x being equal to y, and then the command of x being equal to x minus 2. Finally, you have a precondition of x being greater than 1. Then you have x is equal to x times 3. And of course, this is just a simple example, x being greater than negative 3, which is also maintained through the execution of that command. In the second slide on Hoare triples, we have two simple facts about them, basically where the postcondition is true theorem and where the precondition is false theorem. So once again, we have P and Q as assertions and C as a command, and then for all ST, QST, mapping to PCQ, we have that the postcondition is true. And the Hoare precondition false, once again, we have P and Q assertions, C for all ST, but then we have not PST. So we can see that for the postcondition, the precondition is something different than from what is expected. So in that case, the precondition is false.
Once you've made your assertion formally, you need to use proof rules using Hoare logic. The goal is to show that Hoare triples are valid. You use the compositional method mentioned above, where there's this correspondence between your program and your proof and the different sub syntactic structures made use of by your program have sub-verifications in your proof. The main fundamental rules of Hoare logic are Hoare assignment, Hoare skip, Hoare sequence, Hoare if, Hoare while, and Hoare consequence. The Hoare assignment rule is maybe the most important, given how often we need to use assignments and check they've been done correctly in our programs. Oftentimes we want to skip a part in our program or continue executing without actually changing a state, and that's why we need Hoare skip. Hoare if is the rule that we use when we want to use conditional statements and show their correctness. Hoare while is the rule when we're using loops and we want to show their correctness. Hoare consequence is used when there is an implication or conditional and we want to change either for syntactic reasons the precondition or postcondition to something that's sort of logically equivalent. And Hoare sequence is this idea that it's largely used that if you have one rule that maps, say, state A to state B, and another rule that maps state B to state C, it can sort of sequentially show that if these are done sort of sequentially, that state A maps to state C.
Finally, in the proof rule slides, we address the author's handling of the different forms of commands in IMP. The first that we see is the theorem Hoare assign. So for assignment, this addresses simple statements with preconditions and postconditions, such as y equals 1, and then the command x equals y, and then the result being x equals 1. Or for example, we could have the precondition being y plus z equals 1, the assignment being x equals y plus z, and then the postcondition being x equals 1. And finally, another example, you could have the precondition a equals 1, x is assigned to a in the command, and then x is equal to 1. So we can see in the theorem Hoare ASGN, you have that q, x, and a. So basically, it's a mapping from precondition to postcondition, where the assignment and the precondition is carried out through the command and is then also seen in the postcondition. Secondly, we have the theorem Hoare skip. So this is the simple case of skipping and not actually executing a loop or any sort of conditional statement. So we want to assume that the precondition is false, or rather that the condition is false at the beginning of the execution, so then the body of the statement would never occur at all. So it's functionally like a skip. So we can see in the Hoare skip theorem, P skip P. So you're just literally going from the precondition to the postcondition. So we know that the test for true never occurs, and you never get to the Q postcondition. Finally, on this first proof rule slide, we have a sequencing. So we would have an example, there could be a command C1 where P holds in a state where Q holds, and then C2 where Q holds in a state where R holds, so then P would map to R. And in the way that they've shown it here, it's just inverted. So C2 is that Q to R, C1 is that P to Q, so you can see P goes to Q, Q goes to R, so P simply goes to R. In the second slide on proof rules, we have the if statement. Despite it being the longest theorem, it's actually quite simple. It's just a conditional statement. So that BASSN is an evaluation for whether or not B is Boolean true. So we've got P, ST, and BASN, BST goes to C1. And then we've also got, if there's a negation of that, BASS and BST goes to C2 with the negation of that truth statement. So then the test is test B, then C1, else C2. We can see that if B is true, it goes to C1, else it goes to C2. Finally, on the last page for the proof rules, first we have Hoare while. So this is essentially a looping construct. So we can see here it's the syntax of while B, do C, and. So you need P and B to be true in order for this to execute. As soon as P is true and B is not true, that's when the loop is exited. So you can see there that's what's being tested is also that BASS and B, the Boolean assignment of B. While that is true, the while loop will continue. It will do C, and then it will end as soon as P continues to be true. The precondition must continue to be true in order to get the postcondition. But if that Boolean assignment of B proves to be false, that is when the while loop will be executed. And finally, we have a consequence here. This is more of a structural theorem. So there's been sort of a strict assignment between the precondition and the postcondition, and what this addresses is any sort of possible weakening of them, wherein you could substitute them to still have a valid triple. So the Hoare consequence that is shown on this slide is actually a combination of two Hoare consequences that are not shown. The first of which is Hoare consequence pre, where it's shown the precondition is P prime, and then the command to Q, and we simply show that P is equivalent to P prime, so then P can be a precondition for a command to be executed and result in Q. So just to clarify a little bit, what we're trying to prove is that P prime can successfully be integrated into a command where Q is the consequent, and we merely need to show that P and P prime are equivalent so that we can then get P consequent Q. And simply the inverse of that is shown for the other Hoare consequent post, in which the precondition P, command Q, and Q prime are shown, and then we just have an equivalent statement where Q prime is shown to be synonymous to Q, and then we can get P, command Q as well. And that's shown in a Hoare consequence. That's why we see for all P, P prime, Q, Q prime, and it's shown there, the directionality between going from P prime, command Q prime with those two equivalence statements, and then finally P, command Q being the precondition and the postconditions.
Key to the idea of proofs using Hoare logic is decorated programs. This is the idea that we can take a program and decorate it with the proof assertions itself. We can do this because of the compositional proof structure we've talked about, that mirroring between the parts of the program and the parts of the proof. In this way, the correctness of the program is encoded into the program itself. The basic idea is you have the program text interleaved with different assertions. To check that the program really is valid and that the proof holds, you check that if each command is valid and locally consistent with the assertions that are nearby. Finding proofs is straightforward for the most part. You have a given specification and you need to find the right assertions for it to decorate that part of the program. These usually are straightforward from the part of the program and the Hoare logic that we've studied so far, except for loop invariants, which are often difficult to find.
Decorated programs. This theorem helps us prove a decorated program. We start by defining the function. In this case, it's the simple example from the text, reduced to 0. This function will take any positive integer and recursively decrement it until it returns the value 0. Our theorem here, to simply see if this function is correct, is trying to prove that if the precondition invariant is simply the primitive value true, and then the program runs, the postcondition is that x will be equal to 0. Within the proof itself, we first use unfold on the function reduced to 0 to get the elements of its definition. Obviously, we need to apply Hoare while, but we can't do that with the postcondition in its current form, so we use Hoare consequence post to transform it, and then Hoare while. Hoare while begins the iterative loop, which preserves the invariant, which will be addressed in the next section. However, this time it is the precondition which blocks us, and we must apply Hoare consequence pre before Hoare assign. The next step is fairly straightforward. We simply have to prove a trivial implication, in this case a clear conditional, if line 2, then line 3 in our decoration. Since line 3 is simply true, any value for line 2 will satisfy. Our unmodified invariant and the negated guard form the termination condition. As long as the guard is true, the while will loop recursively. As the QED proves our initial hypothesis that the final state of the program will be that x is equal to 0, we see that the theorem is correct.
Loop invariants are difficult for the same reason that induction proofs are difficult in mathematics. You can strengthen the invariant, which gives you a stronger assumption to use in your proof, but this makes the loop postcondition, the thing you're trying to prove, even harder. There's a systematic way to go about this, which gives you sort of a rough algorithm to find these loop invariants. The idea is you use your knowledge of the program and Hoare logic to come up with a sort of hypothesis or guess as to what the invariant should be. You then are going to check it against these invariant conditions that we're going to talk about. The conditions for an invariant to be valid are it has to be implied by the loop's precondition, implied by the loop's postcondition, and preserved by loop iterations. And so you check your hypothesized condition and you see if it passes all three of these, you have a valid invariant. If it doesn't, you try to reason about why it failed on which of the conditions to generate a new invariant, and then essentially you keep doing this process iteratively until hopefully you finally find your invariant condition.
Finding loop invariants. The theorem to prove parity correct begins with two lemmas. The first, greater or equal to, deals with a recursive call back to parity. It proves that if x is greater than or equal to 2, it will run the program again after decrementing it by 2. The proof is fairly straightforward. We use induction on x to generate the subgoals, and destruct instead of case to apply it to every possible value of x. QED, the lemma is proven true. The less than parity takes care of the other possible condition where x is neither greater than nor equal to 2. In this case, the if statement is not 2 less than or equal to x, and the then statement is the parity is simply x. The full theorem for parity correct begins with the statement that x is equal to some natural number m, runs the while loop, and returns x such that x is the parity, that is, the even or oddness, of m. The proof is very nearly identical to that for greater equal, with the order of command shifted, no rewrite, and an omega. In the proof for parity correct itself, we once more must transform both the pre and post condition before we can apply Hoare while, just as in decorated programs. The cases for our precondition and postcondition are laid out and proven, and we found an invariant that was exactly strong enough that it could be implied by the precondition, could imply the postcondition, and remains preserved by each iteration of the loop for all x.
Another topic that is tied into this is this idea of weakest preconditions. This is related to the sort of decorated programs. The idea is that Informally, a weakest precondition is the easiest assertion to satisfy that guarantees some postcondition will hold after a given command. And there's a formal statement of it as well.
Weakest preconditions. In the first example, we prove the weakest precondition of x defined as y plus 1, returning the postcondition x is less than or equal to 5, is indeed y is less than or equal to 4, completing the Hoare triple. We first show that it is a valid assertion, transforming the precondition before we can apply Hoare assign, then simply introducing the state and h and ending with an omega. Once we've proven it valid, we need to prove it's the weakest. We start by unfolding Hoare triple so that we can use the elements of its definition. The state p' is introduced so that we can show it implies the state p. The second example takes the Hoare assign rule and checks it to make sure the precondition within it is, in fact, the weakest. Just like the prior example, we split the proof into two individual cases, valid and weakest. Valid at this point is almost trivially true, as we can simply apply Hoare assign without even the usual step of transforming preconditions or postconditions. As for the weakest, by unfolding Hoare triple as well as assign sub, we get the definition elements which allow us to prove that p' implies p in all cases, and the proof is valid. The final example is a callback to the first part of Hoare, once again proving that a precondition, this time in Havoc, is the weakest. We must bring back h-imp briefly for our proof. We unfold the elements of Hoare triple and Havoc pre, and then introduce a number of elements and states to clean up our subgoals. H applied across our states lead us to our final assumption and constructor, proving that for all states, the precondition of Havoc is the most easily satisfied. Formal decorated programs. Finally, we provide an example of a decorated program raised to formality. As can be seen, this ultimately makes the final proof fully automated and simple. The initial decorated command of the precondition is given in the context. Then, throughout the decorated definition, each postcondition is given a formal command. This reduces the needed work of proving the theorem down to simple logical and algebraic formulae. With all that out of the way, the proof is nothing more than an introduction and a verify before being proven true.